Welcome to another deep dive, and this time we're going quantum. We're going to be talking about simulating some pretty complex systems.
Many body systems, to be exact.
Yeah, many-body quantum systems, the kind of stuff that really pushes the limits of what our computers can handle.
Absolutely. And it's not just theoretical. This has huge implications for things like, well, maybe even creating new materials. Like, imagine designing the next generation of superconductors.
Okay, now we're talking superconductivity, always a hot topic. But before we get too ahead of ourselves, let's lay the groundwork. We've got a fascinating article from Nature here.
Quantum many-body simulations on digital quantum computers.
Right, state-of-the-art and future challenges. It's like a roadmap for where this whole field is headed.
And it gets pretty deep into the weeds on how we can use quantum computers to tackle this challenge. Which, by the way, is a challenge because, well, it's not easy to simulate the universe.
No kidding.
Yeah.
But seriously, why are these systems so hard to simulate on a regular computer? Like, we've got supercomputers crunching numbers all the time.
Right, but the problem is, when you get down to the quantum level, the amount of information you need to keep track of explodes. It's like, imagine trying to describe every single grain of sand on a beach. But now, imagine every beach on Earth.
That's a lot of sand.
Exactly. And every single grain is doing its own quantum thing, interacting with all the others. Classical computers just can't keep up.
Okay, so that's where quantum computers step in, right?
Right.
Using the weirdness of quantum mechanics to, I guess, fight fire with fire.
Precisely. Quantum computers use these things called qubits, which can be in these weird superpositions, like both 0 and 1 at the same time.
Yeah, that's always mind-boggling to me. But how does that actually help us with these simulations?
Oh, because they can be in these superpositions, qubits can actually represent the state of a quantum system much more efficiently than a classical bit.
So it's like they're speaking the same language as the system we're trying to simulate.
Exactly. It's like having a Rosetta Stone for the quantum world.
Okay, that makes sense. Now, the article talks about two main approaches, analog and digital quantum simulation. What's the difference there?
So analog quantum simulation is kind of like building a scale model of the system you want to study. You use, say, trapped ions or ultra-cold atoms to directly mimic the behavior of the target system.
So like a mini-me of the system acting out all the quantum interactions.
Pretty much, and it's been pretty successful in certain cases, like simulating some basic properties of materials.
But it sounds like it might be tricky to scale up, right? Like, how do you build a mini-me of a really complex system?
That's one of the limitations, yeah.
Yeah.
Plus, analog simulations can be very sensitive to noise and imperfections in the experimental setup.
So it's a trade-off then. What about the digital approach?
Digital quantum simulation is more like traditional programming. You use quantum gates, which are kind of like logic gates in a classical computer, to manipulate the qubits and perform the simulation step by step.
So it's like writing an algorithm that tells the quantum computer how to mimic the system.
Exactly, and this gives us a lot more flexibility because we can program in any kind of interaction we want. We're not limited by needing to find a physical system that perfectly matches the one we're interested in.
That sounds promising.
Hmm.
But aren't we still in the early days of quantum computing? I keep hearing about this NISQ era, which doesn't sound all that great.
Yeah, NISQ stands for Noisy Intermediate Scale Quantum. It basically means that the quantum computers we have today are still pretty small and noisy.
So not exactly ready to simulate the universe just yet.
Not quite. But we are starting to do some really interesting things with them, and researchers are working hard to develop algorithms that can work well on these NISQ devices, even with all their limitations.
Okay, now you've got my attention. Algorithms designed for noisy quantum computers. How does that even work?
Well, one of the most promising approaches is something called variational quantum algorithms. These algorithms are kind of a hybrid between quantum and classical computing.
So like a tag team, where each type of computer does what it's best at.
Exactly. The idea is to use the quantum computer for the parts of the calculation that are really hard for classical computers, like representing the quantum state of the system.
And then the classical computer comes in to help out with the rest.
Right. The classical computer is used to optimize certain parameters in the algorithm to make sure the quantum computer is doing its job as accurately as possible.
Now, I've heard of this one algorithm called the Variational Quantum Eigensolver, or VQE. It sounds pretty intense.
It is a powerful tool, that's for sure. VQE is particularly good at finding the ground state of a quantum system.
And the ground state is like, what, the lowest energy state? Why is that so important to know?
It's important because a lot of the interesting properties of a system are determined by its ground state. Think of it like the system's default setting.
Gotcha. So if we can figure out the ground state, we can start to understand how the system behaves at its most fundamental level.
Precisely. And VQE has already shown some early promise in doing just that, especially for small molecules.
Okay, I'm starting to get the picture here. But we've talked about different approaches to quantum simulation, and now there's all these different algorithms. And on top of that, there are a bunch of different quantum computing platforms out there, right? Like superconducting qubits, trapped ions, photonic circuits. It's like a whole zoo of quantum technology.
It is a bit of a zoo, yeah.
Yeah.
And that's actually one of the big challenges in the field right now, figuring out which platform is best suited for which type of simulation.
So it's not a one-size-fits-all kind of thing.
Definitely not. Each platform has its own strengths and weaknesses. Some are better at handling noise, while others are easier to scale up to larger numbers of qubits.
Okay, so we need to pick the right tool for the job. But it sounds like we're still a ways off from being able to simulate really complex systems, right? Like the kind of things that could lead to those breakthroughs we were talking about earlier.
We are still in the early stages, that's for sure. But the progress is happening fast. And who knows what the next few years will bring.
Well, on that note, let's dive into some of the potential applications of these quantum mini-body simulations. I'm curious to hear what kind of problems we might be able to tackle in the near future.
Let's do it. Okay, so we've got all these different platforms and all these different algorithms, but how do we actually measure progress? Like, how do we know if a quantum computer is good or not?
Yeah, good point. I mean, some of these platforms have over 100 qubits. Isn't that enough to do some serious simulating?
Well, not necessarily. You see, it's not just about the number of qubits. It's also about how well they work together.
Ah, so it's like a team effort. You can have a bunch of players, but if they don't have good chemistry.
Exactly. And in the quantum world, that chemistry is really fragile. It's affected by things like noise and errors, which can make the qubits lose their quantumness.
So a qubit with a lot of errors is kind of like a player who keeps fumbling the ball.
Haha. Yeah, kind of. And that's why there's this idea of quantum volume. It's a metric that tries to capture not just the number of qubits, but also how well they can actually be used for computation.
Makes sense. So bigger isn't always better. It's about finding that sweet spot between quantity and quality.
Exactly. And even with the best quantum computers we have today, that quantum volume is still pretty limited, which is why it's so important to develop those error mitigation techniques we talked about earlier.
Right, those clever tricks to squeeze as much performance as possible out of these NISQ devices. Can you remind me how those work again?
Sure. So one technique is called readout error mitigation. It basically tries to correct for errors that happen when we measure the qubits at the end of a computation.
So it's like the qubits are trying to tell us the answer, but their speech is a bit slurred.
Haha. Yeah, I like that analogy. And readout error mitigation is kind of like a speech therapist trying to decipher what the qubits are really saying.
Clever. And what about that other technique, zero noise extrapolation? That one always sounded kind of magical to me.
Yeah, it's a pretty neat trick. The basic idea is to run the simulation multiple times, deliberately adding in different levels of noise each time.
Wait, add more noise? Why would you do that?
Well, by seeing how the results change as we crank up the noise, we can actually extrapolate back to what the result would be with zero noise.
Ah, I see. It's like figuring out where the target is by looking at how the arrows land when you're aiming with different wind conditions.
That's a great way to put it. Of course, it only works if we have a good understanding of the noise itself, which is a whole other challenge.
Okay, so we've got readout error mitigation, zero noise extrapolation, and you also mentioned this thing called optimized circuit compilation. How does that fit into the picture?
Right, so optimized circuit compilation is all about making the quantum circuits, which are the sequences of operations we perform on the qubits, as efficient as possible.
So it's kind of like finding the most elegant way to choreograph a quantum dance.
I like that analogy. The goal is to minimize the number of operations, reduce the amount of time the qubits are exposed to noise, and just generally make the circuit more robust.
Okay, so we're pulling out all the stops to make these simulations work. But even with all these techniques, we're still a ways off from simulating really complex systems, right? So what can we actually do with these quantum simulations in the near term?
Well, I think it's important to remember that even if we can't simulate everything perfectly right now, these simulations can still give us valuable insights.
So instead of trying to get exact answers, it's about gaining a better understanding of the underlying physics.
Precisely. We can use these simulations to test our theories, explore different scenarios, and maybe even discover new phenomena that we hadn't even thought of before.
Now we're talking. Discovery is what science is all about. So what kind of systems are we actually able to simulate right now?
One area where we're starting to make progress is in simulating exotic materials. Things like, well, those unconventional superconductors we talked about earlier.
Oh yeah, those materials that can conduct electricity with zero resistance, but at much higher temperatures than traditional superconductors.
Exactly. We still don't fully understand how they work, but quantum simulations are giving us some tantalizing clues.
But how realistic is it to simulate something as complex as a superconductor? I mean, these are materials with billions upon billions of interacting electrons.
It is a huge challenge, no doubt. But even if we can't simulate the entire material in all its glory, we can still study simplified models that capture some of the key features.
So like a proof of concept showing that we can at least simulate some of the basic physics.
Right. And these simplified models can still tell us a lot about how the electrons interact and how those interactions might lead to superconductivity.
Okay, so we're using these simulations to kind of chip away at the mystery of unconventional superconductivity. What other kinds of materials are we targeting?
Another area of interest is something called spin liquids. These are materials where the spins of the electrons, which are like tiny magnets, never settle down into a fixed arrangement.
So instead of aligning like they do in a normal magnet, they're constantly fluctuating.
Exactly. It's like a never-ending dance of spins. And these spin liquids are thought to have all sorts of interesting properties, like the potential for harboring exotic particles called anyons.
Anions. Okay, now you're really getting into the weird stuff. But this is what I love about quantum mechanics. It's like the universe is just full of these mind-blowing possibilities.
It really is. And quantum simulations are giving us a new way to explore those possibilities, to see what happens when we push the boundaries of what we thought was possible.
But with so many different platforms and algorithms, it seems like it would be easy to get lost in the weeds. How do researchers even keep track of all this progress?
That's where collaboration becomes crucial. The article really emphasizes the need for close partnerships between the people developing the quantum computers and the people studying the quantum systems.
So it's like the computer scientists provide the tools and the physicists come up with the questions.
Exactly, it's a team effort, and that collaboration is essential for making sure we're asking the right questions and using the right tools to find the answers.
Okay, so we're starting to get a handle on some of these complex materials, even if we're not quite there yet. But what about those bigger questions? Like, will we ever be able to simulate the entire universe?
Well, that's a question for the ages, but I think it's safe to say that these quantum many-body simulations are opening up a whole new frontier of scientific exploration.
And who knows what we'll find as we venture further into that frontier. Maybe we'll discover new laws of physics, new forms of matter, or even new ways to think about the universe itself.
The possibilities are truly endless, and I think that's what makes this field so exciting. We're at the beginning of something truly revolutionary.
I'm with you there. And speaking of revolutions, maybe it's time to shake things up and see what the future might hold for these quantum simulations.
Let's do it.
Okay, so we've journeyed through the quantum landscape, talked about the challenges, the algorithms, the hardware, the materials we're tackling. But where does this all lead? What's the big picture here?
Well, I think the article makes it clear. We're on the cusp of something really transformative. These quantum many-body simulations, they're not just about understanding what's already out there, it's about creating something new.
So it's not just about reading the book of the universe, it's about writing new chapters.
Exactly. And one of the most exciting chapters, I think, is the one about materials design.
Mm.
Think about it. We could use these simulations to engineer materials with properties we've never even dreamed of.
Okay, now you're really getting my imagination going. What kind of properties are we talking about?
Well, we've already touched on unconventional superconductors, right? Materials that can conduct electricity without any loss at temperatures that are much higher than what we thought was possible.
Yeah, those are pretty mind-blowing. But you're saying we can go even further.
Absolutely. We could potentially design materials that are even better at superconductivity, or materials with entirely new properties that we haven't even discovered yet. And remember those spin liquids we talked about?
Oh yeah, those materials where the electron spins are in this constant dance.
Right. Those could be key to developing new types of quantum computers, or maybe even lead to breakthroughs in other fields like electronics.
So we're talking about a revolution in material science, driven by quantum simulation.
I think that's a pretty accurate assessment. We're moving from a world where we stumble upon new materials by accident to a world where we can design them from the ground up, atom by atom.
That's a powerful thought. And the article mentions this idea of a full quantum technology circle. Can you explain what that means?
It's this beautiful idea that the better our quantum simulations get, the more they'll help us develop other quantum technologies.
Ah, like new types of sensors or communication devices.
Exactly. And those new technologies will then feed back into the development of even more powerful quantum computers, creating this virtuous cycle of innovation.
So it's not just about building a better quantum computer, it's about building a whole quantum ecosystem.
Precisely. And that ecosystem could have a profound impact on just about every aspect of our lives. Imagine a world with room temperature superconductors, ultra efficient solar cells, or even quantum computers that can solve problems that are currently intractable for classical computers.
Wow, you're really painting a picture of a sci-fi future here. But let's be realistic for a moment. We're still struggling to get these quantum computers to work reliably. How do we even begin to think about building this grand quantum ecosystem?
Well, it all starts with taking those first steps, no matter how small they may seem. And I think one of the most important steps is to foster collaboration between different fields.
So bringing together the physicists, the engineers, the computer scientists, everyone who has a stake in this quantum revolution.
Exactly. We need to break down the silos between these disciplines and create an environment where everyone can share their knowledge and expertise.
Because at the end of the day, it's a common goal, right? Pushing the boundaries of what's possible with quantum technology.
Absolutely. And I think that shared goal is what will ultimately drive us forward.
Well, I have to say, this deep dive has been quite a journey. We've covered a lot of ground, from the nitty-gritty of qubits and algorithms to the grand vision of a quantum-powered future. And honestly, I'm feeling a bit overwhelmed.
It's understandable. It's a lot to take in, but that's the beauty of it, isn't it? This field is so vast, so full of potential, that it's almost impossible to grasp the full scope of what we might be able to achieve.
I guess it's like looking up at the night sky and realizing just how much we don't know about the universe. It's humbling, but also incredibly inspiring.
I couldn't have said it better myself. And that sense of wonder, that drive to explore the unknown, that's what makes science so exciting. And with quantum many-body simulations, we have a powerful new tool to help us on that journey of exploration.
Well, I, for one, am eager to see where this journey takes us. And I want to thank you for being such an insightful guide through this complex and fascinating landscape. I know I've learned a lot, and I'm sure our listeners have too.
It's been my pleasure, and to all our listeners out there, if you're feeling inspired, I encourage you to dive deeper into this field. There's a wealth of information available online, and who knows, maybe you'll be the one to make the next big breakthrough.
And if you have any thoughts or questions about quantum many-body simulations, or if you have your own ideas about what the first thing you'd simulate would be, we'd love to hear from you. You can find us on all the usual social media platforms. Until next time, keep those quantum fires burning.